It's a really big presentation, like 100 slides, but I will try to focus on the most important things. And we don't have to do everything today. It's just like if it is interesting for you guys, and I think it could be. It's sort of a compilation of what I've learned. So in my master's degree, I worked with LCA, life cycle assessment, lots of carbon footprint, water footprint, energy footprint, those kind of impact calculations for engineering systems. And I've been working with some engineering systems, either for civil engineering. My master's thesis was about iron making, new technology in Brazil. And my previous uh, research group worked a lot with water. So sanitation, water, gray water, rainwater harvesting, lots of things about water. So yeah, this is written here. Probably you will be able to understand some things like life cycle and environmental sustainability for buildings. This is my name, Adriano Leao. Leao means lion in Portuguese. It's kind of my nickname, so if feel free to call me Lion if you want. Adriano or Lion, either works. Okay, the main goal here just to present with concepts and some tools associated with environmental sustainability for buildings and construction. And this first part, I'm going to present a little bit about the concepts. Probably you guys don't need too much of that, but anyways, let's just go through it real quick. And some examples, some things that we've been doing there. Some of those became like articles that are already published. Okay, what is sustainability? Environmental sustainability. Throwing things out means throwing things in because we just have this planet. That sort of talk that you guys know. What is a sustainable system? It would be ecologically conscious, economically viable, and socially just. And why we look for sustainability in buildings. So we have the three sides. This one here is the economic, this one here is the social, this one here is the environment. So I'm not gonna stay here for too long. For civil construction and civil engineering, we uh, can have benefits on the uh, prosperity of the society, development. Sometimes I will like think a little bit because I'm trying to translate what I have here. Generating place for people to work, enhance quality of life, public health, and decrease the hungry people, and about protecting the biosphere. And what is this other one? Pollution and resource scarcity. We play important role here, and we should think about that because we don't do that naturally to the positive side. We do to the negative side. So we should like think about this a little bit. So this is really good for the economic side. For the social side, we have some things are positive, some things are not that positive. And for the environment, most of the times we are not doing like the best thing. So we should think about that. That's this big X here. So the economic value is here, the social value is here, the environmental value is here. And which is very important. We think about that because the concept of sustainability has been evolving. And nowadays we think like this. So without us, which means society, we don't have business. If we don't have people, we don't have business. And if we don't have environment, we don't have anything. So actually, we are within it. So we need to care for it. A little bit about the major impacts of civil engineering. So we use 12% of the soil in the world for the anthropic activities. Okay, anthropic means like made by human. 25% of the water, 25% of the waste generation is due to what we do. 30% of the use of resource, feedstock, and raw materials, 33% of the greenhouse gas emissions, and 40% of the electricity generated. This is just us, and the other sectors: agriculture, transport, energy, everything. Okay, some of the tools, life cycle assessment for us to try and analyze it and try to manage uh, this part of the engineering. This is a Brazilian standard here, but we will have like equivalents here in the US. One concept called cleaner production, uh, lean construction. You guys probably have heard of it, but we are going to like to touch a little bit about it. Uh, Material and substance mass flow, eco design. This one here, probably. Anyways, those ones here are those labels that we have in products, green labels. Okay, this is pretty much, I think, the translation. And yeah, these are the Sustainable Development Goals of the United Nations, and we play an important role in many of those: in Hungary, in water, in energy, industry, consumption, responsible consumption, climate change, and mainly here, cities, communities, sustainable cities and communities. So we play like an important role in the um sustainable development goals of the United Nations. Okay, this is the usual model that we have. It's called a linear economy. Have you guys heard of it? Linear economy, circular economy. So uh, what we do mostly is what we have been doing is um, so harvesting resources, processing them, transporting them, using, and then disposing of. And in the end of the day, in all these stages here of the life cycle, we have emissions to water, to soil, to the air, to the atmosphere. Not only greenhouse gases, we have other types of gas that we emit to the atmosphere. So what we try to do here is like to try to circulate the economy more than a linear way of thinking. So recycling, remanufacturing, reuse, and all those sorts of things. So instead of doing this kind of circle and ending in the landfills, we try to keep the nutrients, to keep the substances, materials going on in cycles. That's the main goal now. So yeah, this is the circular economy. Um, yeah. So this symbol here is the institution that I did my master's degree back in Brazil. Okay, so from the perspective of life cycle assessment, and I can like help you guys a lot with this because it's sort of my background. So we have environmental aspects, which are the causes. So it's not gonna be only about concepts, okay? We are going to jump to examples in a bit. Okay, the causes are mining, agriculture, forest exploitation, production of electricity, water, transport, constructions, everything. This causes environmental impacts, which are the first consequences. So depletion of natural resources, pollution, and changing the land use, okay? And the consequence of the consequence, we call this damage. So first impact, in the second place, damage. Damage are, we are worried about the resources, the ecosystem, and human health, okay? This is like the framework of the life cycle assessment. Some of the applications here, and yeah, now focusing on buildings. Here, this word here, edifications, mean like edificações means buildings in English, in Portuguese. Okay, in Brazil, we have those kind of certifications that are labels. The same as we have in those products here that we can take in our hands. Probably we'll have some labels if it's plastic, saying that it's recyclable, say that it's sustainable in some way. We have certifications for buildings. And this one is pretty known, right? LEED, LEED. Have you guys heard of LEED? Right? We have many builds here at UCLA that had the LEED certificate. Yeah, this is, it said like the degree of sustainability of edifications, of buildings, sorry. This certificate was created here in the US, but we have this being applied all around the world, including Brazil. Yeah, and we have like the normal, the silver, the gold, and the platinum kind of certificate. So these levels differs from how sustainable is environmental environmentally sustainable is the building. And what's our product? Our product are buildings and other types of construction, so including infrastructure. But talking about buildings, we can go from level A to level B, for example. Level A, the whole building. Level B, like a unit in a building. So if you think of apartments, so one unit, it's going to be apartment. Systems and subsystems, plumbing, HVAC, electrical systems, and etc. And all the way through materials. So we can think of concrete, we can think of glass, we can think of everything. We can assess them like from the environmental point of view. Okay, applying the general LCA, like sort of discreting a system in stages, applying this to buildings. So we'll have here the design, the project and the design, and then the extraction of feedstock and raw materials. It won't like be necessarily in time, like chronologically before we extract. So it's being extracted now, we are designing now, so it's gonna be merging in somewhere. But yeah, the idea flow is like this. And manufacture, and we always have transport here, construction, operation, maintenance. In this stage here, we have the use, we have retrofit, we have refurbishment, maintenance, energy. This word here is wrong because we cannot consume energy. Energy is too strong, so we use energy. So energy use and consumption of water. Yeah, actually water we can kind of consume because we pollute it. And demolition, okay? So processing of residues and waste and try to recycle whatever we can. So this is conceptual phase, production phase, construction phase, use phase, and end of life. If you have any questions, just interrupt me. I'm trying to go fast because we have a lot to cover, and I don't want to be here like talking like for 2 hours for you guys. I mean, I want to listen you and discuss with you. Okay, the engineering design versus eco design. So what is the goal of eco design? It's like reducing environmental impacts and impacts for the human health along the life cycle of a product, okay? And the design phase thinks about every other stage in the life cycle, okay? And what we think here, so let's try to understand this circle here. So design first, getting the materials, production, logistics, which means transport and everything, use and end of life, kind of. Okay, so we want to apply the principles of eco design here in the project phase and consider all the other, like design all the other stages, okay? We have to think about them because if we don't think about the end of life of the product, it's gonna just end up in the landfill. I mean, which is like the best case if we don't think about it, but probably it can go like to the sea. We have this huge problem now that plastics are all around the ocean, right? And for the materials, we should use less material and we should use material that has lower impact, okay? In the production, use less resources to product. So production efficiency, generate less waste and cause less pollution. In the logistics, optimize the distribution and think of the impacts of the transport. So the closer we are from the source and from the user, the better. Use less resource here in the use phase, cause less pollution, optimize functionality, and enhance the service life. And treat residues, recycle in the end of the day, and try not to send everything to the landfill, okay? These are called end of pipe measures. So just sending everything to the landfills. And all of those here are called pollution prevention, okay? And the idea is having less and less, fewer and fewer residues and try to cycle resources here. Okay, and how can we act? Doing lots of things. Using eco design, choosing materials. So that's why I was telling all you guys. So whenever you have like a trade-off, will I use concrete or will I use steel here? We can always apply like LCA and try to find the indicators. So the carbon footprint is this, the energy footprint is that. This material should be better for this kind of application. And yeah, so we always have to think of, so to maintain a structure, we will need some amount of concrete and some other amount of steel. So we are not compare like 1 ton with 1 ton. We actually need to know how much of this we have here, how much of this we have here for the same function. So we are actually comparing functions, right? Not only like the material itself. So natural illumination is something that we should think of, and the architecture here probably know lot more about it than we do. At least speaking for me, for myself. Natural ventilation, equipment that save water and save energy, rainwater harvesting, gray water reuse. Um, how do I say that? Appliances, more efficient appliances, and renewable energy. So
I got a question.
yeah,
Um, so aren't there a lot of kind of constraints with with the rainwater reuse for rainwater treatment on like a residence?
yeah.
So how feasible do you think that would be to kind of implement in our design project?
Yeah, I think it's perfectly feasible. One thing that we need to do in the first place in the design, we need to separate like the plumbing thing. So the plumbing system, we cannot mix what comes out of the toilet with the gray water. So gray water, so yellow water is water with urine. Dark or brown water would be water with the other thing. And gray water will be water from faucets and sinks,
Right,
not including the kitchen, because in the kitchen we have organic matter, we have fatty acids and all sorts of things. So we really want like water from the sinks, water from the showers, and from laundry machines. So first of all, we need to separate those, and then we can apply. There are some pathways, so some different designs that we can apply, but mostly for like a basic treatment, we want to use them for non-potable uses inside the building.
right.
So for the potable uses, we actually need drinking water. And to get from gray water to drinking water, it's better if we rely on the public system than we try to do it in a small scale. So in a small scale, it's gonna be either uh, maintenance intensive, so it's gonna like bring lots of trouble. It could be expensive. So if we focus on reusing gray water for non-potable uses, it's fine, and it's out there. It's not something new. People are using this.
Yeah.
So from the city that I lived in Brazil, which is called Salvador, like 3 million people, lots of houses will have gray water reused for uh, to using the plants,
Yeah. Okay.
to clean the floor, to wash the car, to even to using the toilet. We can reuse it in the toilet because we don't have much exposure, because human exposure is the main thing, right?
Yeah.
So showering, washing hands, and washing food and cooking food, it are not potable uses. I mean, need potable water and can have a great exposure, and we don't want that.
Right.
Okay, so yeah, it's certainly feasible for non-potable uses.
Okay.
Yep.
Awesome.
Sure. Um, yeah, so lots of things, lots of concepts here. Let's go. So I want to ask you this. So how much do you guys know about recycling, upcycling, and downcycling? So does anyone want to try and provide us with a concept in a very concise way? Yeah.
So I'd say recycling is just kind of straight up reuse for its original purpose or function. And then I would say upcycling is kind of repurposing and almost upgrading it to something that might be a little bit different.
In a higher level, I'd say, yeah.
And then downcycling would be like, taking whatever product that is and kind of breaking it down into its most basic kind of materials or components to reuse it.
Yes, pretty much. So that's in the sense of the origin of this word, it means like repeating the cycle. So that's what it says here. And we aim to reduce the environmental impact. The one thing that we should keep in mind is whenever we recycle a material, it will start accumulating impurities. Okay, so if we recycle it still, we need to know that it is actually accumulating impurities. So in some sense of, you're perfectly right, but in the repeating the cycle, probably for some applications, even for the same application, which means recycling, you probably need to invest some energy or something in the processing because of the processing, the impurities accumulation, okay? And as he said, like upcycling is try to use for a higher level function, and downcycling is just using something that was kind of noble for a very, commonly used material. So here I bring some examples. So if we have an old aircraft and we have two applications here, so we can either use this steel here to store food or to produce the brand new Airbus airplane here. So is this here recycling, downcycling, or upcycling? Are those two here, those two options? So taking steel from here and
well, the first one's downcycling, second one's just recycling. But Airbus is never going to use a recycled metal in their products.
Yeah, definitely. Because mainly because of this here, right? So it loses the properties, which is very important for this application here. But yeah, pretty much this. And for engineering here, so we usually, so speaking about the civil engineering, the construction materials, if you don't know yet, I will let you know now. The whole industry rely on us to store their waste. I don't know if you guys know that, but there are millions or billions of research papers and theses focusing on how to store this kind of waste of this industry here in the concrete matrix or in this ceramic matrix or whatever it is. Also in pavements, okay? So yeah, lots of industries are relying on us to do that. So this is pretty much downcycling because they're using some sort of material that has had a purpose and now just like to be immobilized in our walls. Anyways, this is only like another way to look at it, okay? Retrofit, it means like redesigning old things. So refurbishing inside, incorporating new technologies, adequating for standards to be accessible. Which, for example, if we have a construction that was made like 50 years ago, the standards changed. Now we are more worried about accessibility. So we could use retrofit to try and fit this kind of function here in the facades and etc. So just so you know, some of those concepts, if we don't know yet, you don't know yet. So yeah, just one heads up here, life cycle assessment is not generalization. It is all about like one scenario. So if you do an assessment of a product here, it probably won't be valid for this product being produced in Japan. So the industry is different, their energy matrix is different, everything is different. So I'm not mean to generalize here. So we need to keep in mind that this is pretty much regarding some context or application. So this is sort of, how do I say that? Provocative diagram here. So if I will ask you, Are biofuels more or less sustainable than fossil fuels for cars, for example? Probably everybody would say biofuels, right? So we have an example here that the uh, biodiesel from Brazil, from 100% of soybean, has a greater carbon footprint than all the major fossil fuels in Europe. And this is why. This is because, why is this? I mean, this is because the way we, in this kind of system specifically, we treat the soil. So by changing the soil use, we are actually not capturing as much greenhouse gas from the atmosphere, and actually, instead of keeping the cycle, we are just emitting. So this is accounted in the carbon footprint, right? So actually, our biodiesel in this study here from like 15 years ago, it has a higher carbon footprint than fossil fuels. So this is only a provocation just to say, not everything that we think is sustainable is gonna be sustainable. We actually need to calculate it, okay? These are some the ISO standards for life cycle assessment. 14040, 14044 are the main ones, and many others. We actually have softwares to do those kind of calculations. I know pretty much how to use this one here, Sigma Pro, but probably here in my PhD, I'm going to be using the OpenLCA. Uh, it's written in Portuguese, this presentation, but if you guys want it, I just can email you. I don't really mind. So I said this because I see probably Gavin here taking notes, but you will have it if you want. It's just I will have like the time now to translate it, but you just like it's pretty easy like to translate. If you have any questions, just reach out to me. And we actually have some life cycle assessment software for civil engineering for buildings. So those here, Athena Sustainable Materials, OneClick, eTool, eEnergy Plus.
We have access to OneClick and Energy Plus through the Solar Decathlon competition.
Oh, nice. And actually, this one here, OpenLCA, is a open source software. So it is all either free and we can like do coding if we know how to do it. And actually, the United States Department of Energy, they have a database. So to do LCA, we need two things. Actually, we need mostly one thing, which is data. So probably someone did all the data gathering and analysis for example, the production of 1 kilowatt hour of electricity. So we are not doing that. I mean, if we want to do that, we will spend like 30 years to do one life cycle assessment. So we actually rely on data that is already there. Okay. So the database for our life cycle assessment is the most important thing. And the Department of Energy has its own database. And we can use it in this software here, OpenLCA. So yeah, probably at some point by next year at most, I'll be dealing with this for my research group here. But yeah, I kind of know how to do it. But yeah, so we have OneClick and E2, you said, right? Or Energy Plus.
OneClick and Energy Plus.
Yeah, I think this E2 here is from Australia. Yeah, I don't think it. I'm sure I have it written here. So yeah, I don't know if I say this, but to do life cycle assessment, we need to have a function. So one functional unit, as we say, 1 kilowatt hour, 1 kilo of concrete, one something. And in the basis of this one something, we calculate everything else. Okay. Yeah, this is pretty much it. Let me jump here. So some of the important impact categories, as we say in life cycle assessment, are carbon footprint, and footprint meaning this kind of feed mark, which carries the meaning that the thing that you did before that you actually don't see, you don't look back, but it's there. So yeah, so carbon footprint, so CO2 equivalents. Does anyone know why equivalent here?
Other gases.
Yeah. Yeah, pretty much. So for each environmental category, we'll have one environmental mechanism. So the climate change is all about greenhouse the greenhouse effect, and other greenhouse gas molecules will have different behavior comparing to CO2. So for example, methane, uh, regarding this environmental mechanism, one molecule of methane means like 25 to 30 molecules of CO2. So we can convert all the greenhouse gas emissions into CO2. And actually we will have greenhouse gases that means like 30,000 molecules of CO2. So it really depends on, but the main one is CO2, probably the second one is methane and all the others. So we have like a huge list of it. So we also have the energy footprint. It's basically kind of the same thing, but accounting for all the energy used, including to produce like, so if I have this product here, I have like a plastic and some sort of a resin here. So the energy used to produce one material and all materials here, they are accounted. Also the electricity used, the water used in this process, and the energy used to produce water behind it. So we can translate everything in energy as well. And water footprints, pretty much the water use considering the scarcity of the region. Okay. Okay, another quick question, and we will reach the examples here. What is renewable and non-renewable? Anyone?
Renewable means you can continue to do it indefinitely.
Yeah. What else? Okay, so it's gonna be pretty much the capacity of the earth to renew a resource. So renewable, it's like you said, like indefinitely. It could be considered like infinite. So the sun is gonna end up like in million or billion years. I don't know. I'm not an physicist, but for our compared to our span of life, it is pretty much infinite, right? And fossil fuels are not. So we have limited amount of fossil fuels, and they will take like million years for the earth like to produce this thing again. But when we're talking about trees and water cycle, they are pretty much renewable because as we go, the cycles will run, and it will be like renewed. So yeah, that's pretty much the difference: the capability of renewability and compare it to our span of life. Okay, some examples here. Those guys use LCA to evaluate this building here. It is a library in a university in Canada, and they actually tried. So their facade is made of copper and steel frame, and they compared to the conventional masonry, as we call in Brazil, like ceramics and a plaster. And this other option here was wood. And they actually found that the fuel consumption and the carbon footprint was lower for those. And this is pretty much what I said. When you guys have a trade-off, either using this or that, we can try to use LCA to try and come up with an answer. In the environmental side, okay? So one thing that we cannot forget is cost. So engineering is all about cost, is like the first aspect that we see. So we cannot forget about that. If it's too expensive, people won't do it unless we have standards in laws forcing us. So otherwise, we won't do it. This is a study here, and probably I will invite you here. So if everybody is like this kind of subject, I have this study going on that is pretty much stuck because I don't have the time. So I was comparing the ceramics, the concrete block building units with, we call in Brazil, probably here, ecological brick, which is soil cement brick. I don't know if you guys heard of it, but it can be used like in very like poor communities. So when ceramics and concrete blocks can be too expensive to build a house, you will need only soil and a little bit of cement and water. So this could be an option, and people call it ecological. Why? Because when you're curing ceramics, you're burning biomass and emitting carbon dioxide to the atmosphere. So they gave it this nickname because it won't like emit directly. It won't emit directly, but indirectly it will emit some carbon to the atmosphere. But yeah, and my question was, is it actually ecological? So that's the driver of this kind of thing. And I had all the data. I had some results. I have some results already, but I didn't finish writing the article. So if anyone is interested, we can talk about this. Do you guys know that we have like different cement mixes? So we have the Portland cement, so PC1, which is pretty much clinker, and we have PC2, PC3. The PC3 uses blast furnace slag, substituting some of the clinker, and the clinker is the main material. So in concrete, the major carbon footprint comes from cement, and in cement, the major carbon footprint comes from clinker. So if we can substitute clinker, better for energy, for carbon footprint. So the CP3 is like, Brazil is the country that uses the most CP3 Portland cement in the world. So it's actually much more sustainable than the CP1, okay? Because we can substitute from 35 to 70% of the clinker using blast furnace slag. So yeah, it's just a waste from the industry. We know that this is not, in the end of the day, the best option, but it is a better option compared to what we have today. And comparing CP3 with CP1, we have lower carbon footprint, lower energy footprint, lower depletion of minerals. These are results from LCA, from our group. So yeah, we did like data gathering, treating, and then LCA thing. And these are like the results here. We did lots of other studies, trying to reuse marble waste, and we decreased the carbon footprint and energy footprint of concrete, optimized cement use, recycling the old concrete in new concrete. We actually were able to decrease the footprints here. So yeah, and we can do that for everything. I mean, everything that we can discretize in materials coming in and out and energy coming in and out. If we can put those information in a compiled way in the form of data, we can do those kind of calculations. So for wood, steel, inks, ceramics, glass, aluminum, PVC, whatever, anything. Yeah, this one here is just about energy. So we have lots of electrical engineers here. So probably we don't need to spend too much time on it. Energy efficiency of buildings. We can do like many things. So in Brazil, we use mostly, as we call, electrical shower. And you guys here use probably natural gas mostly, right? So yeah, so those are fair options in Brazil, but you guys use mostly this one here in the US. And also we can harvest energy from the sun in this system here called like solar plus boiler. So it's just, this panel here is not a photovoltaic panel, it's a water heating panel. So we will have it in the, not ceiling, in the roof, and it will harvest energy from the sun. It will heat it up. When we are at night, the boiler here will have a resistance that will turn on. So we will never run out of hot water. But during the day when we have sun, it's gonna save us some energy. And this is pretty much what happens. So it's cold here. It gets energy from the sun during the day. So we have hot water here. And during the night, we have the resistance, okay? Did you guys understand if you didn't know this one? Yeah. And the resistance, electrical resistance is here. So whenever we don't have hot water from the sun, it will turn it on. And in the end of the day, overall, the energy consumption use is lower, not consumption, use. This is an actual picture of it. Before doing my master's degree, I worked as a uh, MEP designer, mechanical, electrical, and plumbing, but mostly plumbing, mostly water. And I actually did some of those here. Yeah, I did some like 100 or so. My brother has a company. My older brother is a civil engineer, so I always had like something to do with him. And as I was telling you before, this here is just like the separation of the plumbing systems. So for hot water and cold water, we need to have separated systems. It's pretty obvious, right? And for gray water, we'll need to do something similar, okay? Uh, for thermic insulation, we'll have wall insulation walls. So this is very used here in the United States, drywall, right? In between the plates, you will have some sort of material for insulation, for acoustic insulation and thermal insulation.
This is an interior wall.
Yeah.
Is there a reason you'd want to thermally insulate an interior wall?
Is there a reason? Yeah, probably. So,
Or is it just acoustic?
sorry?
Or is it just acoustic? Like the
I think probably both. Okay, so if you have like a business building and you have separate rooms, and if we don't have like a central HVAC system, each one has its own. So we don't want to be transferring heat because it's gonna be like inefficient, right? And also, if you have like a room that is close to the windows and a room that is inside, so we will be like transferring heat from the outside to the inside. So it really depends on. We need to like evaluate the energy transfer from the outside to the inside. This is only to call the attention that thermal performance is different from comfort, thermal comfort, okay? So thermal performance means the wall here, it won't let as much heat from one side to the other. And comfort means we need to be comfort. So humans inside the buildings need to be comfort. So sometimes we'll need HVAC, sometimes we'll need heating systems. Yeah. Um, like 40. So
40.
oh
Yeah, it's okay. You can record it in your view and then zoom.
yeah. Just like 10 more minutes. So I want to show like the most important thing.
Thank you.
Yeah. Sorry about that. This is energy efficiency. The architectures here, we need to think about layouts. So natural ventilation. This one here is a ventilated facade. So we have the facade. We have a glass, like as we call a glassy skin, and we have like the possibility to the air to flow from down to up. And when it is going up, it is getting heat from the building and getting it away. Those type of things here that I don't know the name in English, but we actually have lots of those here in the UCLA buildings, right? And refrigeration and heating, HVAC systems, and this inverter is some sort of new technology that is less energy intensive. And yeah, and LED is better than the other technologies. One thing that we are really struggling at is the end of life, because it has some heavy metals that we need to take care of. So we need to keep that in mind. Yeah, so comparing photovoltaics from the regular energy grid energy in Brazil, we'll have like some sort of trade-off here. So to implement the photovoltaics, it will be more energy intensive than just using the energy from the grid, but it will have a payback just like the cost payback, which is probably 3, 4, 5 years for the economic side. And for the environmental side, we have to calculate. But we have like lots of articles on this thing here. But yeah, energy water nexus. Just saying that to produce energy, we need water. Some of our energy matrix is from hydroelectric power, and the hydroelectric power in treatment of water, and pumping water needs energy. So they are like intrinsically connected. This is another study that is kind of stuck. So anyone that is interested, we were comparing this new kind of material for gas plumbing, comparing to copper. And we did all the data gathering and everything, and we need to finish it. And it is promising. It has lower environmental footprints than the usual one. And also, we didn't do steel, which is pretty much used in the industry. So we have room to do more things. And this is the most recent one that in the, and I will finish here. In the previous meeting, I was saying that we also need to think of water saving appliances or some sort. So this simple thing here that has two buttons, one for number one and two for number two, you guys know what it is. So it will save like 3 liters of water for each flush. And we did the calculations here. These are brand new articles that we are publishing. So the payback for carbon footprint is 6.6 years, for energy 4.8, for water footprint 1 month. So all the water involved in the production of this toilet is pays itself in 1 month because of the water saving. And for the cost 3 years, the money that you save, considering the money that you invest on it, the money that you save on water will be like paid back. And this means that if everybody in my hometown, like 600 people, used this, we would save 240 cubic meters of water a year, and saving, no, this is for toilet, for per toilet, and this amount of CO2 and this amount of energy. Yeah, so these are all the graphs and all the flow chart here. So yeah, I think, yeah, this the most important. I said this is gray water. I pretty much answered his question. For color, for microbiological risk for human health, this is all proven that is okay to use for non-potable uses, okay? And rainwater harvesting systems here, we actually also proved that the carbon footprint is 40% less and 50% less energy footprint. If you use it like for 25 years comparing to the water from the public system.
Does it depend on like the actual rainfall in your area?
Yeah, so
So like here in LA, it's not a lot of rain. Is it worth it?
yeah, definitely. So this is for our case study there. So we actually have some rainwater there, which is much higher than here. So as I said in the previous meeting, if we want to implement it, we just need to know where is the site and to look for the rainwater data and just to compare with the demand. So this is like pretty simple calculation that can help you guys with that. Yeah. So sorry about that. I was kind of late. This is too many information maybe for those who don't know about it. And yeah, I'll be happy to take questions after and like to help you guys whenever I can. And just a quick like comment. I'm pretty busy with the PhD, but I really like the initiative, the project. So I will try to help you with whatever I can. Okay.
Is
Yeah.
there any way that you can send this?
Definitely.
Maybe a master or something so we can all get it?
Definitely. Okay. Yeah.
And if you have time, feel free to record the last part of the short rushing through, because I can just edit the video and post it in YouTube and everything else.
Yeah. Sure.
All right.
All right.
While I pause the